Hello, College Algebra student. This video is for Chapter 6.1, Part 2. We are going into explore how we can write the exponential function formula given some points or given some behavior or given some condition. So we introduce what is the formula of an exponential function. It has y equal to a times bx. B is what we call the growth factor. That's the number that you keep on multiplying, and you can understand the growth factor as 1 plus growth rate, because if you think of how you can get a b, you can think of, so a is the initial value, so you can think of you have a, and then you add a times r, right? You're adding a constant percentage. This is called the growth rate, but you would write it as, you factor the a out, so it would be 1 plus r, right? So the first time, and then you do the same thing, 1 plus r, second, third, so this is time. So every time you do one iteration, it is 1 plus r times 1 plus r, and you can call this b. Okay, so b is called the growth factor per time period, and r, the growth rate, is called is the growth rate percentage, the growth percentage per period also. So either one, how you can find out how to write it. So again, initial value. If you know the growth factor, which is very rare, usually they will tell you what the growth rate is. You add 1 to it, it becomes b. Okay, 1 plus the growth rate become b. Growth rate is how much it grows percentage-wise. So there's two cases where we can write this function. One is when initial value is given, a is given, then you write a, and then you use the second point to solve for b. Okay, if a is not given, but you have 2 points, x1, y1, x2, y2, then you plug into y equal to abx and then solve the system. So we're going to illustrate how to do that. For example, this is an exponential function, you can tell, and look, growing up exponentially, shoot up very fast. If it is, linear, it would be very flat. The 2 points would be, you always look at the y-intercept because that's where a is. So you have 0, 3, right? It's very small, so I write it out. And then the other point is 2.518. So we can find an exponential function for this graph. So because 3 is the initial, so this is a, right? I should point to this. So a would equal to 3. So this is the second one. This is x and this is y. So I write y equal to 3 times b to the x. Y is 18, so this is the second point. I write 18 times 3. This is 3 is from here. 3 times b to the power x is 2.5. Right? So how do I solve for b? I divide it by 3 on both sides, so it becomes 6 equal to b times 2.5. So how do I find b? B, root of 2.5. 6. This is not 6 of 2.5. 6 and b looks alike. So in the calculator, what you do is you do 6 to the power. Oh no, not to the power. You should do root, right? So you can do 2.5 and then a root and then 6, and that's how you get it. So let's see. Can I do that? 2.5 and then I do root and then a 6. 2.04 477. So there I have b solved. So the equation is y equal to a 3 times 2.0477 to the power x, and this describes this function. Okay. Do another one. Again, I have 0, 4. 0, 4, this is the y-intercept, so a is 4. And then I have a set of x and y, so I would just plug in y equal to 4 times b to the x, right? 36 is y. 4 times b to the x is 2, right? And I divide 4 on both sides. This is an easier one. So I have 9 equal to b squared. Take square root because b has to be positive as a base is 3. So the function is y equal to 4 times 3 to the power x would describe this function that passed through this point, 2 points. Next one, these 2 points, I don't have a y-intercept. This is xy, this is xy, x1, y1, x2, y2. So what do? I just write it 2 times. Y equal to abx, right? A times bx. So I don't know a, I don't know b. So I would say y is 6 equal to a times b to the negative 2, xy, right? Another y, which is 1, equal to a times b to the what? 2. This is x. So I have 2 equations, 2 unknown. I can use substitution. So substitution, use this one. Okay, maybe I'll just say this. This is equation 1. This is equation 2. 6 is equal to a. B over negative means, b over means b squared. So I multiply b squared on both sides. 6b squared is equal to a. Do you agree? Now you substitute it into the second one. Substitute to 2. So 1 would equal to 6b squared times another b squared. So they're the same base. You can add them. 1 equal to 6, b to the 4th. So divide by 6. 1 6 is equal to b to the 4th. So it's doing the root. b is 4th root of 1 6. So b would equal to, we need more space. So b equal to 4 root of 1 6, 0.6389. 0.6389. You can do more if you want to. What about a? Oh, a is 6b squared. A is equal to 6 times b squared. So that would be equal to 6 times. I use the one that I have in the calculator for b. So it's 2.4495. So the function is very funky. Is y equal to 2.4495 to the power. I think you can write this also if you want to. 0.6389 to the power x. It's outside of the screen. Okay. So that's how you write it. Some application. So eventually, this skill that we have is used to do an application. So for example, you know that in 2008, 80 deers were introduced into a wildlife refuge, and the population is growing exponentially at 14% per year. So this is the growth rate. That's R that we're talking about, the growth rate, not the growth factor, right? So if I know the growth rate, I know B. 1 plus 0.14 equal to 1.14. Do I know initial? This is initial A, right? Oh, I can write my function. F of t is equal to A, 80, B, 1.14 to the power t. T is t years after 2008. So remember, A has to be the 2008 where you start, okay? And so once I have the function, that I can use it to do prediction. If it continue, what would be the number of deer at years 2020? So 2020 corresponds to t equal to 2020 minus 2008. That is t is 12, right? So that means I'm going to do f of 12. That would equal to 80, 1.14 to the 12. So that is what? 80 times 1.14 to the 12. 385.4. these are deer, so round to the whole number, 385 deers. So if they're growing exponentially, adding 14%, it is as if you're multiplying 1.14 every year. So that's still exponential growth because it's greater than 1. Okay. There is another one that's depreciation. So let's do this one. We have a car that's bought at year 2000. It should be year 2010 at $25,000. So this is initial, right? A, initial. The value depreciated to 13,050 in year 2014. So we don't know the growth rate, we don't know the growth factor, but we have another number. So what is time here? So this is 2010 is time equal to 0. 2014 obviously would be time equal to 4. So you can imagine yourself having a number of 0, 25,000 and then a 4, 13,050, right? 4. So you just solve it as if we did this before. So this is our A. So we say y equal to 25,000 b to the t. So x is 4. That is 13050. That is t and y. You plug it in. So that would be 25,000 times b is the unknown. Time is 4. So you times it 4 times, it becomes this. So we will solve it. So divide by 25,000 on both sides. So 13050 because we want to do root, right? 25,000. That's equal to b to the 4th. You don't even need to cancel it because you're just going to do the 4th root. 4th root of this big number, 13050 over 25,000 would equal to b. So what do you do? Put in the calculator. 4th root of 13050 divided by 25000. So if you don't know how to do your root in your calculator, just email me because I don't know what calculator you have. So b is a fraction. So because that's what we expect, it is decreasing. 0.84999. So let's say round it to 0.85, right? So my function would be f of t is equal to a. A is $25,000. And then 0.85 to the power t. Okay, so if the value continue to drop because it's keep on depreciating, what is it at year 2020? So at year 2020, t would be 10, right? Because t equal to year 2010 is our 0. So we would just do f of 10, plug in 25,000, and then 0.85 to the power 10. So 25000 times 0.85 to the power 10. Put everything in one shot in the calculator. Don't round it intermediately. Oh, it only depreciated to $4,000. 0.86. So to the nearest cents, this is what it depreciated into after 10 years. So so this is how you write an exponential function if you're given some data. It will be useful, right? Sometimes we know that things are decreasing exponentially. You can use 2 instances of values to figure out the function and then use it to predict what it is later on.